So it is a new beginning for us. And this chai, a small introduction about chai and why, is, as you all know, it provides an informal space and it provides an informal space where interesting scientific issues can be discussed outside the traditional academic setting. It provides an opportunity for people who are curious about science to meet the scientists, interact with them, ask questions, and share their own thoughts. At Nehru Science Center, also, we strongly believe that science communication is not only about presenting scientific facts, it is also about creating opportunities for conversation and dialogue. We are also celebrating this National Space Week with the inauguration of a AI prompt art exhibition, which is a one of its kind exhibition, first time happening at Nehru Science Center. This exhibition brings together science, technology, art, and imagination. It explores artificial intelligence, how it can be a new medium for creative expression and scientific storytelling. I am particularly glad as both these initiatives are happening together here today. The why, that is from the chai and why, asking questions, and beyond that, what if? Your imagination can take you wherever you want. So I extend my warm welcome to our distinguished guests, our colleagues from TIFR, the scientists, educators, students, parents, and artists all along. I sincerely hope that today marks the beginning of a meaningful and long-lasting collaboration between Nehru Science Center and TIFR, and it inspires many more conversation, questions, and creative idea. Once again, a very warm welcome to you all. I am now pleased to welcome on stage Professor Arnab Bhattacharya, Director, Homi Bhabha Center for Science Education, to deliver the welcome address.
Welcome. So it's a pleasure to be here for Chai and Why. She's already told you about Chai and Why, so I don't need to repeat that. Let me just start by introducing our speaker for today, Professor Mayank Vahia, who actually probably has given too many talks on this stage. He's given several Chai and Whys as well, probably after me, the second largest number of Chai and Whys. He is an astronomer, was in the Department of Astronomy and Astrophysics at TIFR for several years, where starting from space shuttle missions to probe various aspects of the universe, ending with archaeoastronomy, seeing what historical records tell us about what did our predecessors know about the universe. He has covered everything. So with that, I think let's get Vahia on and get started.
Hello, hello, hello. Yes, yeah. Yes, sir. First of all, thank you to Nehru Science Center for inviting me, for Arnab for inviting me. Um, it's a pleasure to be here on this stage, and Kenneth have just said that I must have given more than 25 talks on this stage. We have had fun. We have had lots of fun here, and it always feels great to be back home. This has been my second home for a long time, 40 odd years. And today, at the inauguration of the Space Week, I'm going to talk about. Let's go next one. I'm going to talk about going beyond the Earth. I think in the last 4 or 5 decades, there have been so many different approaches to going to space that if I was to try to convert the entire world scenario, I don't think 1 week would suffice because there are programs which are simply magnificent. Ours are also very good, and I will show them to you as soon as I get my. Yes. So I'm going to restrict myself only to ISRO's programs and try and talk to them or talk about them in detail. There are very few countries that are as wide-ranging a program as we do. China has, America has, but there's no other country that has this kind of a wide-ranging program that India has. That India does it also very cost-effectively is a different part of the story. We will come to that in a minute. So I'm going to talk about going beyond the Earth, only focusing on India's effort, and obviously ISRO is the agency we talk about. So why go to space? I mean, going to space has a lot of advantages. Space is used for communication. I hardly need to tell you these days when you have satellite telephones and all the Wi-Fi, etc., or at least all the internet, etc., works on satellites. You can do long duration space observation. If you want to know what is happening on the Earth over decades or over at least years or decades, then satellite is the only way of doing it, because you can fly aircrafts in principle and get the data, but aircraft has to fly. Even if you take one of those new ones which can remain stationary in space, the drones, etc., they only last for a few minutes to a few hours, and they won't go very high. So you won't see much through other means. Satellite, on the other hand, once it is launched into space, a good satellite will work somewhere between 5 and 10 years. And with the same detector, same camera, if you're getting signal for 5 or 10 years, you know it's stable, you know it is good. You don't have to worry about changing performance and so on. So satellite is very useful for long-term observation. You can do resource management, find out where there are rains, no rains, find out water availability, find out crops, and so on. You can do disaster management. And if there's an earthquake, etc., it's not always easy to reach the spot on the ground or communicate with people on ground. So satellite give you the first images. And the most effective use, or the first major use was done when there was an earthquake in Bhuj in 2000, I think, 26 January, where the entire effort of relief was coordinated through satellite images, because you knew where there was a major damage, which roads were open, which roads were closed. There was no trial and error. You knew exactly how to make effort reach where it needs to be. It is used for defense for obvious reasons. You can make out what your enemies are up to, and you can guide your own weapons through satellites. In space sciences, India has done very well. In astronomy, we have had large number of payloads, one dedicated satellite for astronomy from near Earth, and then we have had missions to Moon, we have had missions to the Sun, we have had mission to Mars, and we will talk about some of these things as we go by. And we have visited different worlds. Moon is something that we have visited well. Venus, Mars, we have had a look at, and hopefully in the coming years we will look at other planets also. So there's a desire from ISRO to send a mission to Venus and so on. And now that the government has said that ISRO should launch some 30 satellites within the next 5 years, we will now have plenty of more opportunities to go to different places. Is it easy to go to space? And the answer obviously is no. And the reason why it is no is also very complicated. That is the reason why not many countries have a space program, because it costs. That D should be rupee sign, but anyway. It costs somewhere between 5 and 8 rupees for every gram of weight that you want to launch into space, which is a factor of 1,000 cheaper than what you can do from America. So it costs about 5 to 8 rupees per gram. Nobody obviously has a satellite which is 1 gram. You're talking about 3,000 kilograms plus, which means the launch cost can go anywhere between 150 and 400 crores, depending on the kind of vehicle you're using and so on. So going is not so easy. You need an economy that can spare 400 crore rupees plus all the infrastructure and everything. So it's not so easy. Also, there are other problems. A rocket is small. A typical satellite would be about 2 meters or 3 meters, 2 meters generally. in height and about a meter, meter and a half in diameter. And that little volume must fit in your entire satellite, including solar panels and everything, must fit into that little volume. So weight is much more difficult to get. So places, things like space station are built by sending multiple small missions and then merging them together. The only other vehicle that can take much larger payloads, of course, your space shuttle, which is no longer in operation. So putting objects on top of a rocket means that you have to be very, very miserly with weight. Every little gram counts. Its power source is solar power. So you have to depend on your solar cells and their efficiency and so on to get the power. Only a couple of payloads that have gone up have used nuclear energy, and United Nations frowns upon sending nuclear energy because if you have an accident, that nuclear dust will spread all over the place. So generally it is forbidden to have nuclear power in space. So the only source of power is solar cells, which obviously means it is limited. The launch is very violent. If you think somebody driving a fast car is going very high, you can imagine for space you have to go from 0 kilometers per hour to about 0 kilometers per second to 8 kilometers per second in a matter of about 16 minutes. So the launch itself is violent. Not only that, the launch rocket we will see typically tends to be about a few tens of meters or 10 meters or so. And at the bottom of it, you have the rocket launching. And the top is where the satellite is. So the vibration that the satellite feels are also very violent. So the launch itself is not only high acceleration, but extremely violent. It takes the sun directly in its heat. If you think 40 degrees in Mumbai at summertime or 38 degrees in Mumbai at summertime is bad, you should see what the satellite feels. 80, 90 degrees it can take when it is facing the sun, and in 45 minutes it will go behind in the earth shadow and suddenly plummet to 40, 50 degrees minus. So the temperature variations it sees are remarkable, and therefore it gets heated and cooled very fast. It faces intense radiation in the environment because of the fact that there is no atmosphere to protect you, and so the solar radiation will come and hit you right on your face. So your satellites have to be protected against that. And the satellite obviously cannot be repaired. In the history of human space missions, only one satellite has been repaired, which is Hubble Space Telescope, and now they are trying to repair one more, Spitzer, I think. But essentially, of the thousands of satellites that we have sent up, only one was repaired, and that is because it was an extremely expensive piece of equipment. That's why it was repaired. In general, if a satellite stops working, you just forget about it. And yet, a good satellite is an extremely powerful tool to have and allows you to do a lot of things which you cannot do just terrestrially. So let us look at the space. There are two parts to space. One is going into the space, which is the rocket, and putting something into space, which is a satellite. And this is the India's first satellite, Aryabhatta, but that is just a symbol for satellite payloads. So just to go to history, India launched its first rocket in 1963, which was a sounding rocket. It would go to about 70, 80 kilometers up in the atmosphere and would come back in a matter of minutes. But even then, good science could be done. Several PhDs have come from the research that was done there. Eventually, Government of India set up ISRO in 1969 under the leadership of Vikram Sarabhai, and then things really took off. In 1975, we launched our first satellite into space, Aryabhatta, 360 kilograms in a very odd orbit, 398 by 409 kilometers, 50 degrees inclination. When I talk to you about orbits, you will realize the importance of this. It lasted in space for a year, then eventually re-entered the atmosphere, got burnt up in the atmosphere, and was lost forever. The first satellite that we launched was on satellite launch vehicle number 3. It was called Rohini 1B, which was the smallest satellite launched by any country. It was just 30 kilograms in weight. It was again launched in a very odd orbit of 305 to 919 kilometers at an inclination of 45 degrees. It weighed just 35 kilograms. It re-entered in about 10 months, and that was the end of Rohini 1, but at least we established that we can launch with satellite. Before that, in 79, we had made an attempt which had failed. So Rohini 1A had failed. Rohini 1B is the one that went into space in 1980. So good 45 years ago. These are the ISRO's centers that we have. Most of them are in the south because our satellite launch happens from south. Sriharikota is where we do our launching. Tirupati is where we have Atmospheric Research Center. Mahendragiri is where we make our rockets, the propulsion systems are there. Tiruvananthapuram is where we have rocket making facility, including liquid propulsion and all that. Bangalore is where the headquarters is. Hassan is where there is a control facility from which they talk to the satellite. Ahmedabad has Space Application Center. Bhopal has a master control facility from which they control the movement. In Dehradun, we have remote sensing agency. And in Shillong, we have another dedicated Northeastern Space Application Center dedicated to studying Northeastern region using satellite data. So this is more or less the set of establishment. Then there's an office in Mumbai, office in Delhi, and so on. So how does a rocket move? Obviously, it can't move on wheels. It essentially, what it does is, if you have a mass at a certain velocity, you eject gases at very high velocities, and Newton's law of motion will tell you that if you emit gases at very high velocities, you can move forward. So essentially what you have, you obviously can't just put gases and put them in, because then you can in principle take a gas cylinder and if you release the valve, it will in principle try to move, balloons try to move. But over here, you will need a system which is more efficient, which produces much more amount of liquid heat and hot gases than you normally do. And I'll show you this picture in detail. But essentially, it's a question of fuel, something that burns the fuel and the fuel flame comes out, and then you have a rocket. And there are two kinds of rockets that people use. One is a solid fuel rocket. So it's essentially wax. It's a wax where you don't have a wick, but you have a hole right in the center. And in the center is where you put a flamethrower, and that flamethrower will burn the entire wax structure. And all the hot gases that are released will come out from the bottom of it, and you will get forward momentum. Solid rockets are very good for bulk lifting, but there is very little by way of control that you have. So if you want to control the movement of a satellite or movement of whatever is on the top of the rocket, you need liquid fuels. Where there's a liquid oxidizer, liquid fuel, the two come together and burn. This is less efficient in terms of weight, heat produced per unit weight. This is more efficient, but this doesn't have the subtleties of maneuverability which the liquid fuels have. And no single rocket is strong enough to take a satellite into space. So rocket, when we talk about a rocket that is launched, it is essentially multiple rockets sitting on top of each other. So you have a combination of solid and liquid rockets sitting on top of each other to make a four-stage rocket. So this is what PSAV looks like. There is a rocket at the bottom, which extra boosting rockets if necessary. Then there is a second rocket over here, which consists of liquid fuels. A third one, which in this case is also liquid. There is a liquid-solid combination, liquid combination, and eventually you have a payload on the top. And this is about what, 10, 12 meters or so. So you have four kinds of rockets sitting on top of each other in PSLV. But as far as liquids are concerned, the most efficient liquid is when you mix hydrogen and oxygen to give you water. So hydrogen oxygen is the most efficient fuel you can think of, except that hydrogen and helium, water, oxygen are both gaseous at normal pressures and temperatures. So if you want to carry a decent amount of hydrogen or oxygen and hydrogen into space, you have to cool both of them to very low temperatures. And low temperature technology is called cryogenic technology. So your rocket fuel center, just to go back, there's hydrogen and oxygen over here, and which means both are under high pressure and low temperatures. So the temperature here will be minus 200 degrees or so, while the temperature here runs into 700 degrees centigrade. So you should have a technology which can maintain that kind of a heat gradient, where within a couple of meters or 3-4 meters, at one end you have temperatures of hundreds of degrees centigrade, at the other end you have temperatures of minus hundreds of degrees of centigrade. So it's not a technology that's easy to gain, and therefore these engines are called cryogenic engines. And India uses cryogenic engine in the last stage. GSLV final rocket is cryogenic engine. For those of you who remember history, we were originally going to get the technology from Russia, and America put pressure on Russia, and Russia wouldn't sell it to us eventually. And it took us some time to develop it, but now we have a very good cryogenic technology. These are the satellite launch vehicles India has. This is SLV-3, which took up our first satellite. Then it was quickly augmented with 2 more booster rockets to take a higher weight. It was augmented satellite launch vehicle. I'll come to SSLV in a minute. PSLV is the workhorse of Indian space program. So it takes about 2,000-3,000 kilograms into 800-kilometer orbit, and this is our workhorse. For geostationary satellite, we developed a rocket called GSLV with cryogenic engine at the top, but these are still not heavy enough to take enough weight. Now we have, for satellites in geosynchronous orbit, we have a rocket that can take up to 3,000-4,000 kilogram payload, and that is LVM-3. Now, before we have manned mission, we want to have HRLV, human launch vehicle, which is quite a large vehicle. And this is about 50 meters. So you get an idea about how tall they are. This rocket is an augmented version of GSLV with additional boosters, and on the top there's a slight difference because it will have a capsule with human beings in it over here. So this will take our astronauts to space, and these are the other rockets. SSLV is a creation of Indian Space Research Program to do small experiments. If you have to encourage universities, to encourage private companies, to encourage others to think of doing something in space, we have a special category of launch vehicles called small satellite launch vehicle. And these small satellite launch vehicles are available for commercial use, for experimental use. And in fact, when I show you the launch stations, SSLV ke liye, they're building up a separate launch platform from which these things can go on. So when private space agencies have started coming up, they can initially experiment with SSLV, or if they can even put their rocket at the SSLV launch pad and see how it works before they graduate to heavier weights. So these are the two main launch stations that we have. Both are at Sriharikota. This one is the older one, where the entire rocket was assembled inside this building. India assembles its rockets one on top of the other. NASA does it horizontally and then lifts the whole thing up. We do it vertically, one on top of the other. So the 4 rockets are assembled one on top of the other. Then there is a railing which brings it out, and then eventually you launch it. Then we have another launch vehicle again at Sriharikota, where this is the launch pad. And this rocket eventually assembled, and these are railings are directly connected. So this goes from here to here. So the assembled rocket is taken there. Over here, there are 4 clamping arms which can clamp the rocket, do the final checking, final testing, and then the rocket is launched from here. These large towers are essential to prevent lightning, etc., from falling, so weather purposes. But this is the launch vehicle. And if you look at GSLV, it looks rather majestic. I like this picture simply because it looks so majestic. This is the assembled rocket being taken to the launch station, from where it would eventually fly. To give you an idea about how quick these things happen. Okay, you start at 0 minute 0 second, the first column in the data. The second column is how far up in the space you have gone. Okay, it's just 26 meters, 0.026 kilometers. And this is the velocity. You start with 0, and eventually you end up with 7,000 meters per second, or 7 kilometers per second. The fourth stage takes 109 seconds, 1.8 minutes to launch. The entire first stage with all its rocket, main rocket and the booster rockets and everything lasts only for 109 minutes. The second stage lasts for 262 minutes or 4.4 minutes, and the second rocket is ignited after. So first rocket is launched, the payload, the top coverings are removed, and the satellite then has reached about 3 kilometers into the space, 3.6 kilometers, and that is when the second stage gets launched. The second stage ends, and the third stage starts about 8.2 minutes. The fourth stage is 994 seconds, and the last and the fourth of the four rockets get ignited 16.5 minutes from start, and eventually, the rocket gets put into the place where we want it. So the entire rocket, costing 400 crore rupees, burns up in 16 minutes. The most expensive firecracker that you can think of, and it's and for if I should have pointed that out. The weight of these things are several hundred tons. I think it is written somewhere. This is some few tens of thousands of kilograms, and what we reaches up eventually in the space is a couple of thousand kilograms, 4,000 kilograms. You can launch your satellite into various orbits. You can make it completely horizontal, you can make it completely vertical, or you can make it at an angle. If you make it vertical, then the advantage is that the earth around below you will keep spinning. And so all you have to do is to keep going north, south, north, south, north, south, and the earth will show you its different phases over a period of time. So if you have a 90 minutes orbit, essentially the earth will turn by 15 degrees in that much time. So if you just go north, south, you can see the earth beautifully, and you can cover the entire earth in a matter of 24 hours, actually 12 hours on either side. And that is the common orbit used for remote sensing satellite. If you want to know what is happening to the Earth, you essentially launch your satellite north-south and you can look down. And because north-south is pole to pole, the rocket that takes it up is called Polar Satellite Launch Vehicle, or PSLV. The other useful orbit is this horizontal orbit near the equator. If you fly at the equator, and if you can fly it at a velocity so that it completes one rotation in 24 hours, effectively it is stationary for you. Because the Earth goes around on its axis once in 24 hours, the satellite also goes around in 24 hours. So essentially it is geostationary for you. So this is a geostationary orbit, and the rocket that will put our satellites into geostationary orbit, or the rocket that puts our satellites into geostationary orbit, is GSLV. So you have GSLV rocket which takes them to the equator. The problem is, in order to complete one rotation in 24 hours, you have to go 36,000 kilometers. The radius of the Earth is 6,000 kilometers, and here you have to go to 36,000 kilometers. So that is where it becomes a little tricky. And this orbit is useful for nobody other than scientists, in the sense that space station goes this orbit. Our initial rockets, which were tried, if you remember now, both Aryabhat and Rohini 1B were at a highly inclined orbit. This orbit is scientifically not useful in except one case, where if it's a satellite that is going around the Earth at 24 hours and in an inclined orbit, you can use it very cunningly for communication, and we will see, not communication, for tracking and so on. And we will see when we talk about GPS systems, this is the kind of orbital combination that they use. So inclined orbits are used for GPS because you have multiple rockets, multiple payloads that are flying. Okay, Elon Musk wants to fly thousands of them, so that at any given time you will have multiple satellites in view, and you can do your localization. Taking a rocket that will put you all the way into geostationary satellite is a very expensive affair. So we don't do that. What we do is we launch it in a highly elliptical orbit, and it is closest to the Earth by just a few hundred kilometers, and it is farthest at 36,000 kilometers, 35,800 to be precise. Every time it reaches the top, there are little rockets on the satellite itself, which will fire making the orbit a little more inclined. And over a period of about a week or so, you eventually get a circular orbit at 35,800 kilometers with a revolution period around the Earth of 24 hours. And that is how you get geostationary satellite. So when geostationary satellite is launched, for a week, you don't hear anything about it because it takes them a week to get the orbit correct. And that's how this geostation. So there is something called geostationary satellite, and this orbit, which takes you from few hundred kilometers all the way to geostationary orbit, are called geosynchronous rocket. So the rocket puts our satellite in a geosynchronous orbit when it is at the farthest is 36,000 kilometers. Eventually, it goes into geostationary orbit where it goes around the Earth once in 24 hours, and it is very useful. So India has two sets of satellite design. The upper ones are all communication satellite in geosynchronous orbit initially, eventually geostationary orbit. And the first thing you notice is that they have two solar panels on either side to prevent them from toppling. There is nothing to hold on to in space. So if you have two solar panels on either side, then the pressure from the sun is balanced, and therefore you can fly. The satellite can remain stable. The second thing that you would notice is that these satellites are not very intelligent, in the sense that their only job is to pick up signal that has come from the ground, use solar power to amplify that signal, and send it back on Earth. That is all that they do. So they typically have two antennas, one to receive the signal, then the box in between to amplify the signal, and eventually send it back on Earth. So you can send it from a single point. The signal may weaken, but when you amplify it and send it back, the entire Earth can see it. Now, of course, we put other equipment, transponders, and we put cameras and so on to do additional things. But original purpose of a communication satellite is to pick up the signal from Earth, amplify, and send it back. Then we have a whole series of Earth observing satellites. And these Earth observing satellites are in a much lower orbit, typically about 800 kilometers, with a period of 90 minutes around the Earth. And they all are specialists in camera and a single communication antenna to talk on Earth. And we have made remarkably good remote sensing satellites, which have been used by a whole host of countries, because these are very good. But they are lower Earth orbit, polar to polar, and they can do a lot of pole to pole, and they can do a lot of Earth observing. Once you have good communication satellite, you can use it for telephone, television, business communication, mobile satellite network, global positioning systems, search and rescue systems, and weather forecasting, not to mention disaster warning and disaster management. So it's a very useful satellite to have. And like I said, Earth's remote sensing satellite go in that 10 o'clock orbit. So the way it goes around the Earth, when it looks down, the local time is 10 o'clock. In the daytime, when it's on the daytime, it is 10 o'clock in the morning. When it is night time, it is 10 o'clock at night. The advantage of 10 o'clock is that at 10 o'clock daytime, the city or the human life is fully functional. So you can determine who is doing what, where, etc., in a broad sense of the word. And you can get a very good information about the surface of the Earth using 10 o'clock in the morning. When you do 10 o'clock at night, it is about 3 hours in sunset. So the Earth is now cooled, the initial heat from the surface is gone, and you can get infrared emission from under the Earth. So depending on what is under the ground, that material will differently control the Earth. So if there is an iron ore at the base, etc., you can make out using the 10 o'clock at night infrared cameras. So if you have a combination of optical and infrared cameras, you fly them in 10 o'clock orbit, you get a lot of information. And that's why we fly this 10 o'clock orbits. India has two GPS systems which are active. One is called IRNS, India Regional Navigational Satellite System, which consists of 3 satellites in geosynchronous orbit. Now, they are not geostationary, they are about 20 degrees off, if I'm not mistaken, but at 36,000 kilometers, and they can look at the Earth in one way. And so these 4 satellites are in geosynchronous orbit. They work in pair. One goes up, the other one goes down. And there are 3 satellites which are in geostationary orbit. This combination of 7 satellites gives you the entire global positioning system that you want. The signals, of course, it's at 36,000 kilometers, so it is not as easily available as the GPS on our wristwatches or our mobile phones, but it's fairly efficient. And this is particularly useful for defense purposes because the satellites are quite far, 36,000 kilometers, one going north and south of the equator, 3 on the equator, and therefore you can get a pretty good detailed picture of what is happening on Earth. Recently, one of the IRNSS satellites failed, and ISRO has just announced, I think, 2-3 days ago, that they are going to significantly upgrade the IRNSS because our security environment is changing so much. The second one is called Gagan, where there are 4 or 5 satellites close to the Earth and one geosynchronous satellite. And this combination will give you GPS of the kind that we need for our mobile phones and so on. And this is used largely, the proposal is to use it for transportation. So if you have an aircraft that is landing, or if you have a ship in the sea, in the Mumbai, in the Indian subcontinent region, you can use this to monitor your position. So aircrafts can land and take off based on this Gagan system. So this Gagan system is an entirely civilian system to be used for civilian purposes, and IRNSS is largely for defense purposes, and both are operational. Unfortunately, our government is not good at publicizing, but you don't realize that we have 2 remote sensing systems. Only thing is that they are focused only on the subcontinent. So unlike the GPS satellites which provide worldwide data, this provides only data for the region. We yet don't have ambition to fight the Americans. So you can see the region that it is effectively able to see. And that's good enough for our needs. We had a problem during Kargil when Americans switched off the GPS system and our guided missiles, etc., got into trouble. So eventually India decided to have its own defense GPS system, and IRNSS is a part of that. Then there are space missions. There are space missions that you can use, look at solar system objects, do X-ray astronomy, X-rays from objects, gamma rays from sky, sun and its storms, and unified Earth studies. And India does all of them. I'm not going into the remote sensing data simply because I don't have too much of time. I want to focus on beyond the Earth observation. And the first object, of course, is Moon. We have had 3 missions to Moon. Before Gaganyaan, Chandrayaan went up, there have been 123 missions to Moon from Earth. 123. Since out of that, 56 have failed and 67 have succeeded. Now the number is 140. So there's 120, there have been another 17 launches. Out of this 56, out of this 123, 52 were missions which are flyby. They just sort of took a look at the moon and then went further on to do something else. 68 were orbiters which orbited around the moon. 10 were landers, the Apollo series, Apollo 1 to Apollo 13 or 14. 9 were manned missions, 2 were orbiters, 4 landers, and 3 landers with rovers. And India has one of the lander with rover with Chandrayaan 3. In Chandrayaan 1, we just had a lander which was plunged on the ground. There have been 10 missions that have included landing or crashing on the moon, and India has had 2 of them. The first attempt to go to the moon was made by America in 1958, August 17, but it didn't succeed. The first successful mission was by the Soviet Union at that time, which is 1959. Chandrayaan 1 was launched on 2008, October 21st, and that was the 115th mission at the time. It was a small mission, 1,380 kilograms, out of which 675 kilograms reached the moon. So the rest of it was fuel which was burned while reaching the moon. It was in a 100-kilometer orbit around the moon. It was launched on October 22, 2008 and reached the moon on November 9. So it took good 16 days to reach, and I'll come to why it took 16 days. It lasted for 312 days. It was originally supposed to last for 2 years, but after 312 days, apparently the system got heated and some components failed. But it is incidentally still going around the moon, dead weight. It had a small 29 kilogram impactor, which was thrown on the moon on November 14. It was just an impactor, and the idea was just to see how the landing happens. The mission ended on August 2009. It had 5 instruments from India, 6 from abroad, NASA, European Space Agency, and Belgium. Its primary objective was to create a 3D map of the moon. And it was a highly successful mission by any stretch of imagination, and it gave us some beautiful images. Now, the problem that India has that we don't have a very heavy rocket. We can do 2,000-3,000 kilograms at a time. So the orbit we use is this. We fly first rocket in geosynchronous orbit, but then instead of firing the rocket at the top, we fire the rocket at the bottom, making the orbit more and more elliptical until it becomes so elliptical that eventually it takes a moon transfer orbit, and eventually it goes to reaches the moon. Just to start this movie again, just to start, it is 274 kilometers by 24,000 kilometers, and it will fire only when it is over here. And eventually, lunar transfer orbit, it takes at 386,000 kilometers by 247 kilometers. And eventually, the moon is in fact below the picture when this rocket took off. And eventually, the moon traveled up there, the payload traveled up there. And originally, it was in a 200 kilometers around the moon, and then it was gradually lowered 200 kilometers around the moon. But this is how the orbit went. And this is what costs us whatever 10-15 days to reach the moon. Americans all have rockets which are big enough to take their object directly to the moon, and therefore they are faster. They can do it in 3-4 days. We take about 20 days to reach the moon, but we can do it with a much cheaper rocket. Okay, so this is what Chandrayaan-1 looked like. This is the little object that fell on the moon. 11 experiments of various kinds, and it looked at the moon. So this is the first picture of the moon taken by Chandrayaan-1, distance of 311,000 kilometers. And this is what Chandrayaan has become eternally famous for. Each orbit saw a strip of this. That is why it is in strip form, and some of the strips are missing because the satellite died before completing the mission. But the blue color is the name of the game, as it were. Blue color indicates water. And so we realize that there's a lot of water on the moon in the north and the south pole. And many missions had gone before that, but none of them had looked for water. The Chandrayaan was specifically designed to look for water, and it found that there's plenty of water on the north and south pole. Plus, there are other minerals. Blue color is one kind of mineral, hydroxyl molecules, which is water. Green is surface by measured in infrared. And red is the one that shows ion-bearing region. So you can see the moon, like Earth, is not homogeneous. It is heterogeneous with various kinds of material. But the claim to fame was water, identifying water, and that has established a first for the missions to moon. If you look at the surface of moon, you won't see the water, which is why we had missed it so far. But Chandrayaan-1 had a special payload which could identify hydroxyl molecules, OH molecules. So every time the sun went and hit that place, the water would evaporate, and that evaporated water would be seen by Chandrayaan-1 moon mineralogy mapper. And they identified that a region like this, in fact, had a fairly widespread amount of water. If you took a meter cube of this soil and squeezed it, you would get about a liter of water. So this sponge was actually carrying a lot of water, which came as a pleasant surprise to us. Chandrayaan-2 was a follow-up mission to the moon. Originally, it was built on the experience, obviously, of Chandrayaan-1 with increased capacity for weight and everything. and now the PSLV was changed to GSLV Mark III, which means the satellite could be heavier. It was launched on 2009. It took us 10 years to launch Chandrayaan 2 compared to Chandrayaan 1, because Chandrayaan 1, 2, we wanted to put a payload on the surface with a buggy. And originally Russians were supposed to give, and for various reasons, the Soviet Union disintegrated into Russia, and Russians were a little unsure, so they withdrew from their commitment. And so we had to develop that moon rover ourselves. It took 10 years to do that, but eventually it went up in 2019. It reached the moon on August 20. It tried to put down a lander on September 7, and did not succeed, which is a part of space mission. So Chandrayaan 2 mission had an orbiter which is still going around, the lander which was supposed to land, and a rover which was supposed to go there. Unfortunately, this lander had problems. But interesting thing is that the orbiter was so well made and so sturdy that when Chandrayaan 3 was sent up as a follow-up of Chandrayaan 2, we did not send our orbiter. We used the Chandrayaan 2 orbiter to control Chandrayaan 3 lander. And we focused entirely on the lander in Chandrayaan 3. And Chandrayaan 2 itself, of course, gave us an enormous amount of information about where to land and how to land. But we don't appreciate that this orbiter was made so well that a few years later, when Chandrayaan 3 took off, it used the same orbiter. So Chandrayaan 3 consisting of a lunar orbiter, which was Chandrayaan 2, but it had its own lander and rover, Pragyan and Vikram. And the scientific goal included studies of the structure of the moon, understanding the water molecules, and the orbit of lunar, and to continue with this 3D mapping of the moon. This is where it landed, in the southern pole, because this is where we knew there was a lot of water. So it was designed to land at a latitude of 70 degrees south and a longitude of 20 degrees east. These are the first pictures that Chandrayaan, so this is still Chandrayaan 2 mission pictures. This is where it was supposed to land, and this is the kind of image that it gave us. It was supposed to land close to this impact crater, and you can see how rough the surface is. So landing was always going to be a very big challenge. This one is 73 kilometers across. It looks like a little dot here, but when they're sufficiently close, this is what that crater looked like. When Chandrayaan 2, I'll just go back to the original picture of the orbiter. Okay, just focus on this orbiter. The lander. The lander had 4 legs, and out of ample caution, ISRO had put 5 rocket motors to slow it down as it landed. One of those 5 motors did not trigger properly. And the result was that the payload was imbalanced. It wasn't sure its altimeter was giving correct numbers. It was not sure where exactly it was. As a result of which, it fell on the moon with a much greater impact. Its legs could not hold it, and the payload broke. Okay, and this is the picture of where Chandrayaan 2 was supposed to land, and all these green pieces and blue pieces are part of the Chandrayaan 2 mission's components, which are scattered all over the place. This is a picture from Earth. Okay, so green indicates the confirmed pieces of Chandrayaan 2's lander, and others are probable pieces. So Chandrayaan 3 was immediately designed. Like I said, Chandrayaan 2, we were so sure of the quality of the orbiter that Chandrayaan 3 didn't even have an orbiter. It just had a huge propulsion system to take a relatively heavy payload this time to the moon, and this thing eventually came and crashed on the Earth. But this part went and landed on the moon. It was launched on 4 years later. It reached moon after 42 days, and the lander and rover reached the surface of the moon successfully. And Chandrayaan 2's communication system was used to control this Chandrayaan 3. I remember I was here when the Chandrayaan 2 launch happened. Yes. This is the region where it landed. Various moon craters are there, but you can see how terribly complicated this is, and which was not easy. This is the picture of Chandrayaan 3 on the surface of moon. Now no longer any scattered pieces, nice single one piece of Chandrayaan 3. And this is the picture from Chandrayaan 3 releasing the rover on the ground. So these are the wheels of that rover. This is the rover, this is the communication antenna, and this is the shadow of the lander. And these are the first tracks of it. And the wheel, of course, had a little bit of national emblem and so on. So it made a track with emblem and so on, and it went around a little. Now the problem is that when night falls on moon, it can become really chilly, minus 140 degrees or something. Which means that if you want a rover that will survive the night of the moon, you would have to put additional heaters and you have to put all kinds of systems to keep it warm during that night period. And we didn't have the weight or the weight to put that kind of additional weight. So this lander was, this rover was designed to move only for 14 days, and it worked very well for 14 days. And then when the night fell, essentially its components froze. It provided three. So what all have we learned from Chandrayaan missions? We have learned that it provided 3D map of the Earth. It established the moon surface as being dynamic. We have seen Earth moonquakes, and we have seen movement of liquid below the surface and so on. It has a good quantity of water on it. It has good mineralogy map of the moon. It permitted us to establish the kind of minerals that exist on moon: calcium, silicon, aluminum. And most exciting results were to look at the moon mission. The next is Mangalyaan. Mangalyaan was a mission to moon. Before that, there had been 49 missions. More than half of them had failed. The first one is October 10, 1960. Never made it. The first successful mission was this time by NASA, 1964, and it landed. It reached Mars on 1965. 13 flyby missions have gone to Mars. 16 were with landers. 4 missions included rovers. 27 of the missions have failed. More than half the missions have failed. Mangalyaan was launched on October 5, 2013, reached Mars on September 24th, 2014. It traveled 200 billion kilometers to loop that. And it makes Arnav very angry when you compare this with the cost of traveling 20 billion kilometers by car. Okay, it's phenomenally less. Because it's a silly comparison, and I agree it's a silly comparison. Anyway, it landed, it went into Mars orbit around 200 billion kilometers around Mars. This is what the Mars orbiter looked like. The solar panels are much larger because the sun is much fainter, and it had the fuel tank and cameras at the bottom. The major objective was that if you want to reach Mars, you are essentially hitting a 5 rupee coin at a distance of 1 kilometer when you yourself are moving at 6 kilometers per second. So you are moving at 6 kilometers per second, like a 5 rupee coin trying to hit a grain of sand, which is itself at 6 kilometers per second. You are at 24 kilometers per second. So the mergers are not easy. That we succeeded in the first attempt itself is a very impressive achievement. All other agencies failed once before they managed to reach, and only Soviet Union and Russia, America have tried. Other countries have not tried. China tried to send a mission to Mars just before Mangalyaan did, but it never made it to Mars. Mars orbiter is designed by ISRO to make the machine capable of earthbound maneuvers like the ones that we do for Chandrayaan. It cruised for 300 days from Earth to Mars, then enter the orbit around Mars, and in orbit phase in the Mars, it should be able to collect the data and incorporate autonomous features to handle it. Because Mars is so far, it takes about 15 minutes for the signal to go and come. So you cannot possibly control the movement of that payload from Earth. The machine had to identify it for itself where Mars was, locate where Mars was, correct its velocity, correct its movement, reach Mars, and eventually get into orbit around Mars. And all that had to be done autonomously. It was entirely the onboard software that was supposed to be, because as it approached Mars, its velocity was faster than the escape velocity. So it would have bypassed Mars and gone further off. So it had to slow down by correct amount in order to get the orbit that we did. And we had to learn about deep space communication, navigation, mission planning, and management, which was not easy. In fact, the first signals of the success of Mangalyaan did not come from a control center in India. It came from Australia, where one of the Australian antennas was at the correct place at correct time to look at Mangalyaan land approaching Mars. Earlier, there have also been stories. European Space Agency, when they tried to send a mission to Mars, it was Indian GMRT which was at the correct time at correct location, and they maneuvered its movement and eventually saw that payload crash on Mars. To explore Mars surface for morphology, mineralogy, etc., and these works have been going on. This is how the orbit took off. So you have the Earth over here. It departed on December 1, 2013. When Earth was here, the Mars was here. And it took this orbit like we talked about in lunar missions. And eventually, it left the Earth on 1st December and it took this journey. By the time the Earth had turned almost 300 days, so 365 days would make a year, this is 300 days. Mars was over here and it landed over here. And they both met on 24th September 2014. And therefore, that 300 days. This is the last picture that Mangalyaan took of the Earth, and you can see beautiful cloud covers and everything. December is a winter months, and you can see how this is November 19, 2013. And then it turned itself to, it essentially went to sleep actually. And then woke up, it woke up twice or thrice in between. It looked at the stars and it knew what pattern of stars it should be able to see if it is in the correct path, made minor corrections to its path, and eventually went to sleep again. And it did that 2 or 3 times before it reached eventually Mars. Just before reaching Mars, it again switched off. The star patterns that it was expecting to see are the correct star patterns, so it knew where it was. And then it took a picture of Mars, which was exactly what we were expecting. And that is where Mangalyaan landed on Mars. We have lots of very pretty pictures of Mars. Unfortunately, the rover that is NASA has sent has overwhelmingly better pictures. But this is this is a huge volcano on Mars that you can see. These are the canals on Mars you can see, and a lot of things are there. But we have to cut short. It was so much important that our 2000 rupee note, I haven't seen one for a long time. But anyway, on the 2000 rupee note, there was a Mangalyaan picture on it. Then we have had a series of other missions that everybody is not very familiar with. The first is this lunar mission. Now, lunar mission is a very peculiar mission. It is at L1. If you look at the Earth, if you look at the Earth over here, and if you look at the sun there, you can imagine that now Earth alone is controlled by the gravity of the sun. But in between Earth and sun, the gravity of Earth and sun both play a role in deciding the orbit. So the orb, a few million kilometers, about 1.5 kilometers towards the sun from Earth, you have a point which will also have a 365-day orbit around the sun. We have a 365-day orbit around the sun. So does this Lagrangian point have around the sun. But the advantage is that this point is always between sun and Earth. Which means if you put something over here, all the time it is looking at the sun. And a gentleman called Lagrange worked it out for the first time. So this is called a Lagrangian point, where the gravity of sun and Earth is such that its revolution period around the sun is also 365.25 days, and therefore it is stationary with respect to the Earth, but it is not obstructed by Earth's eclipse. It can look at the sun all the time. So in September 2023, we launched our Aditya 1 mission. It took several months to reach. In January 24, eventually it reached there. This is what the Aditya mission looks like. And the Aditya mission has a magnetometer, 2 solar panels. Now the solar panels are much smaller because the sun in fact is brighter, and it had multiple other payloads for various observation of the sun, and some magnificent results have come out from this. I don't have the time to do it, but this is the pictures. There are the various pictures of the sun that Aditya produced. Aditya has been doing very well. But at least these are missions that we have heard of at some stage or other. There are other interesting missions that ISRO has taken up, about which there is very little general knowledge. So let me cover those. 10 minutes, yeah. The first is crop modification. So what ISRO did was to send up a module with plants in it. Okay, so they wanted to germinate and grow two-leaf stages of plants to see whether plants will grow in space. And they had 30 millimeter by 40 millimeter simulator box inside, and they successfully demonstrated that plants can grow. So they took these beans and grew them in space. It was entirely on a satellite near Earth orbit, and eventually it would crash and die. But we could show that even in the zero gravity of near Earth orbit, plants can grow. The other interesting experiment that India did was in January 2025, when two satellites were made to merge with each other. Where two satellites launched at different times at different place, eventually would be flying different orbits, but they would gradually come together and merge together. And this experiment was done on January 16th. It worked so well that they actually connected it. They were happy it connected, disconnected, made them go a little further away, and then come back and meet again. So there were two bounces that were done. And that's space docking of satellite, which would be crucial, for example, when we start talking about making a space station of our own, which should not be very far into future. So transferred electric power from one dock to the other. It did composite spacecraft control, payload operations, and unlocking was done. And all this was done when the satellites normally move at about 80 kilometers per second around the Earth. Well, this had to come down to 10 millimeters per second, because if they banged into each other, they would break each other. So these extremely low relative velocities have to be obtained. Even the overall velocity had to be 80 kilometers per second, otherwise it would fall on Earth. But the relative velocity had to be reduced to 10 millimeters per second so that they could gently merge into each other, and it worked spectacularly well. The other major experiment that was done 12 years ago was the satellite re-entry mission. This is the place where the payload is kept. There was a Cartosat satellite on the top, but below that, there was a space re-entry vehicle. And this is what the space re-entry vehicle looks like. And it was launched and it was brought back on the Earth successfully. So we knew how to bring material from space back on Earth. And this is how it was collected. This is the heat shield that would have been removed at the last minute. And that obviously you can see here. This is our planned manned mission, first human flight. And this top cone and this top cone are similar technologies. Slightly larger, the rocket now is augmented PSLV. 3 astronauts will go on it. The satellite, the autonomous cabin will be 3.7 tons in size. Gaganyaan will go up hopefully next year or later this year or early next year. GSL Mark III heavier version will take it. It was crew module was tested in 2014, like I showed you. 2 unmanned flights have been successful. Now we are scheduled for a manned flight. And ISRO is so confident that last week again there was a news that we are going to start setting up the entire facility to train astronauts into space environment in India itself. This was our first man on moon. I feel bad that he has been forgotten. Rakesh Sharma went up on a Russian mission. Since then, they've also gone up in American missions and so on. But he's the first man who flew into space from India. These are the 4 men who are supposed to, 3 of whom will go up in Gaganyaan to go around the Earth. The other future plans of ISRO include an X-ray astronomy mission, a NASA-ISRO collaborative mission of low Earth orbit for Earth observing, SpaceX for docking experiment. We want to make sure that we understand it fully. Mangalyaan 2 is planned. Gaganyaan missions, of course, are on the pipeline. Shukrayaan, mission to Venus is planned. And a new satellite spaceport is being planned to help private agencies and for ISRO small satellite launch vehicles. And then there is Samudrayaan to look at the Earth and the water bodies on Earth for Institute of Technology. One of the biggest problems in space, of course, is the junk. And massive amount of junk. Each of this blue dot is a piece of junk going around the Earth of size at least of a few millimeters in size, smaller than we cannot even track. And this is what it looks like today. It is bad enough today, and we have lost, humans have lost a couple of satellites because of this debris collision. If you have seen, there was a movie, Gravity, I think, which had this collision of this debris. And in near future, with Elon Musk wanting to send thousands of satellites and so on, this space debris is going to look like this. So unfortunately, like the greenhouse, we have not really worked on this problem. And various space agencies have sort of paid a kind of lip service to this removal of this garbage, but it has not been removed. There are no serious plans of removal of this garbage. Private space agencies, now India's private space agencies are coming up in a big way. There are about 500 suppliers who supply various components to Department of Space. But eventually in 2021, government said, now we'll start up an Indian Space Association for private agencies. All major players, Larsen & Toubro, Nalco, OneWeb, MyMap, India, Vagere, have all come forward to make missions. And these are some of the things that have been tried. So Indian Space Research Organization 64, Hindustan Aeronautics has been participating. But New Space India, Larsen & Toubro, this can't be 1938. This too, 2020. Godrej. Okay, the original companies were established whenever they were, but these are all players who have now started working on space program over the last 2-3 years. There are several reasons for long-term settlements. The last part that I want to come to is about going to moon on a longer term. There are lots of reasons for going to moon. Mining is one, working on space is another, but it's not going to be the easy because we have better understanding. We now have some understanding of how to live in low gravity, but we have to worry about it. Better astronomical telescopes can be made. You can mine the moon. You can understand how to live in low gravity and so on. So there is a lot of good reasons to go to moon. And when we see the exhibition on AI generated images of space, you will see most of them are focused on moon, various kinds of possibilities for moon mission. Going to moon mission, several agencies are planning to fly to moon. Moon is not so easy to go to. The radiation there is miserable. Water now we know thanks to Chandrayaan-1, but power is going to be an issue because when it cools, it really cools. The temperatures are harsh, can be anything between plus 120 to minus 130 degrees centigrade. Lunar dust we now know is extremely sharp, sticky, and electrically charged. So you need to worry about those kind of things. And supplies, of course, will have to come from Earth. We are not still good enough to set up a self-sustaining biosphere on the moon. NASA has a major plan for a moon base by 2032. Chinese and Russians are working on another international space station. European Space Agency has a program. But last week, NASA, August 5th, 6th, there was a joint meeting of NASA and ISRO, where India has been now formally invited to join NASA's program. Because of the success of Chandrayaan-3, they know India can now make landers and India can also make very reliable transport vehicles. The base will evolve initially as robotic mission. Eventually, habitable zones will be set up. Living modules will have to be they'll have to be pressurized. There'll have to be an artificial biosphere to grow food. And when you go and look at the exhibition that is to be inaugurated in another 55 minutes, you will see how we need to control our environment. We need to create artificial biosphere. We need to create a recycle of waste. We need to worry about radiation protection. We need to worry about thermal protection. We need to worry about emergency handling systems and removing people. We need to worry about power supplies, especially at night time and so on. And this is what we guess moon missions would initially look like, eventually settling into a nice housing arrangement under some rock on moon to help us save us from various radiation and so on. And so the bottom line is that India's space program is one of the most extensive programs in the world. It has done very fine in remote sensing and communication. It has also extensive experience in space programs, including astronomy and planetary exploration. And Indian space scientists are looking for more and interesting challenges in space sciencing in the future. And India also wants to have not just Gaganyaan, but actually have a manned space station because it has turned out to be a very useful factory for creating specialized chemicals in zero G gravity and so on. and a lunar base in collaboration with NASA. Thank you very much.
Can we have the house lights? So, thanks, man. That was fantastic. We're going to take a short break for chai. There is chai outside. Please have a cup of chai and come back. But before you go, reminder that August has a fifth Sunday. So there is a fifth Sunday special chai and wai session, which is live from the lab in TIFR. This is about cold atoms. You will learn how we can cool atoms to extremely low temperatures and then do experiments with them. That's happening on 2 weeks from now, the fifth Sunday of August. And sorry, I'm very sleepy. I've just been watching the moon actually. I went to watch a solar eclipse. The first 29th of August. The first
30th of August.
30th of August. Okay.
Yeah.
The first Sunday of September, we will be as usual at Prithvi Theatre, and there the topic is about the physics of how you get power at a plug point. The physics of your plug point. I know the speaker. It's me. The getting energy actually is very simple. I mean, Einstein told us that E is equal to mc squared. So, it's a very simple equation. If you want light from the sun, it's E equal to h nu. That's just photons that give us energy. But actually getting energy from your plug is the same physics that makes it so easy, makes it very difficult. So how do you generate power and how do you get it to your plug point at home is going to be the focus of the Chai and Wai at Prithvi. And a month from now, we will be back here. I don't know if we'll be in the auditorium or we'll be in one of the other rooms over there. We'll let you know what that topic is. But the next two Chai and Wais, one is from the lab, that's online only. 30th of August is on cold atoms, and then physics of your plug point. That's at first Sunday of September at Prithvi Theatre. On that note, let's take a quick break for chai. Have chai. I'm sure you have lots of questions for Mayank. We'll allow him also to just have some chai and get energy, and then he'll answer all your questions. We will have to wrap up by 12:55 because at 1 o'clock we need to inaugurate this other exhibition. Remember, this chai is also part of National Space Week, so don't go away.
If you go away, my life becomes simpler. If you go away, my life becomes simpler.
You got hit by bots online.
I don't know how to do that.
Got hit by bots online, and some crazy guy was talking about how everything exists and all that stuff.
Right.
So many